All right, let's get right into it. We're about to explore four of the most important, most elegant equations in all of physics. And I'm not just talking about some dusty old rules. You can think of this as the fundamental source code that literally governs electricity, magnetism, and light itself. This is the story of how our modern world was written.
So what are those rules? How do these invisible forces that power our entire civilization, how do they actually work? For centuries, they seemed like totally separate, kind of mysterious phenomena. But as it turns out, they're all part of one beautiful, interconnected story.
So to understand the story, we first need to meet our two main characters. On one side, we have the electric field, we'll just call it E, and on the other, the magnetic field, B. The easiest way to think about these is as invisible fields of influence that fill all of space, constantly pushing and pulling on electric charges.
Now, what's really amazing is that for decades, physicists like Faraday and Gauss had been figuring out bits and pieces of how E and B behave, but it was a total mess, something like 20 different really complicated equations. Then, in 1865, a Scottish physicist named James Clerk Maxwell came along and, in what can only be described as an act of pure genius, he managed to boil all of it down into just four elegant and incredibly powerful equations.
Okay, so let's start with the first two rules. You can think of these as the static rules. They basically describe where the electric and magnetic fields come from in the first place, how they begin and how they end.
Now, to really get these first two rules, we need to understand a concept called divergence. And don't worry, it's easier than it sounds. Just imagine the fields are like the flow of water. Divergence simply measures if a point is acting like a faucet, with water spreading out, or like a drain, with water converging and going in. So a faucet has positive divergence, and a drain has negative divergence. Simple as that.
And this idea of divergence brilliantly shows the first major difference between our two fields. Gauss's law for electricity says that electric fields do have sources and sinks, and those are electric charges. But then you look at Gauss's law for magnetism, and it says magnetic fields have zero divergence, no sources, no sinks, no faucets, and no drains.
So, this first equation, Gauss's law for electricity, tells us that electric charge is the source of the electric field. That first part, the del dot E, don't let it scare you. It just means the divergence of E, how much it spreads out. And the equation says it's equal to rho, which is just the amount of charge. You can see it right here in the animation. The glowing blue field lines just radiate straight out from a positive charge. That charge is the source pushing the field out. That's positive divergence. The second equation, Gauss's law for magnetism, is just stunningly simple. Del dot B equals 0. That's it. It means the magnetic field has zero divergence. Always. There are no magnetic charges, no magnetic monopoles that act as sources or sinks. Magnetic field lines don't start or end anywhere. Just look at the animation. They always form these perfect, continuous, closed loops. See how every single orange field line that leaves the North Pole loops right back around into the South. It's just one unbroken, continuous flow.
Okay, so we know where the fields come from, but now we get to the dynamic connection. These next two rules show how E and B aren't separate things at all. They are actually locked in this intricate dance. And trust me, this is where the real magic happens.
The first two laws were for situations that were static, unchanging. But what happens when things start moving? What happens when the fields themselves actually start to change over time?
Well, the answer is Faraday's law of induction. The left side, del cross E, represents something called the curl of the electric field, which is just a way of saying how much it swirls or circulates. The right side, that Maugative of B over dt, represents how fast the magnetic field is changing. So you put it all together, and what do you get? A changing magnetic field creates a swirling electric field. Look at the animation. As that orange magnetic field pulses and changes, it induces that swirling blue electric field in the wire loop. That simple principle is behind every single electric generator on the planet. So, a changing B field creates an E field. Does it work the other way around? Yes, but it turns out there are two ways to do it. The first way was already known, moving electric charges, a current in a wire, that creates a magnetic field that swirls around it. But Maxwell realized, for the laws to be perfectly symmetric and beautiful, there had to be another way. He predicted that a changing electric field, even in empty space, must also create a magnetic field.
And that brings us to the fourth and final equation, Ampere's law, with Maxwell's absolutely crucial addition. Just like before, the del cross B on the left means a swirling, circulating magnetic field. And on the right, we see it's created by two things. The J part is an electric current, moving charges, which you can see happening on the left. But that second part, the dE dt, that was Maxwell's stroke of genius. It means a changing electric field also creates a swirling magnetic field, which you see on the right. This was the final critical piece of the puzzle.
So let's put it all together. With that last piece of the puzzle, Maxwell had assembled a complete and, frankly, perfect theory. He had unified electricity and magnetism into a single, comprehensive force, electromagnetism.
You know, it is really hard to overstate the power that's packed into these 4 lines. With just a handful of symbols, these elegant equations would go on to describe a huge slice of our physical reality. And here they are, in all their glory. You've got the 2 Gauss's laws on top telling us where the fields come from, their sources, and the 2 curl laws on the bottom tell us how they interact and change one another. A changing B field creates a curling E field. That changing E field then creates a curling B field. It's a perfect, self-perpetuating dance.
Now, here is the big reveal. Maxwell realized that this dance, a changing B field creating an E field, which then changes and creates a B field, and on and on and on, this would create a wave that could travel through empty space. And when he calculated the speed of this predicted wave using his equations, he found it was exactly the known speed of light. The conclusion was just inescapable, and he wrote it down in his 1864 paper. I mean, listen to his own words. Light and magnetism are affections of the same substance, and that light is an electromagnetic disturbance. In that moment, he had discovered the true nature of light itself.
So why does this matter to you and me? Because these 4 rules don't just describe the visible light from the sun. They describe the entire electromagnetic spectrum. The radio waves that carry your favorite station, the microwaves that heat your food, the Wi-Fi signal connecting you to the internet right this second. It is all just Maxwell's equations in action.
So you see, what started as this messy collection of 20 different observations was unified into just 4 lines of beautiful, predictive mathematics. And it really leaves you wondering, if the vast complexity of electromagnetism can be described so elegantly, what other simple, profound laws are still out there just waiting for us to discover?